physical chemistry, and today I'm going to run through a few undergraduate level, upper high school level chemistry questions. So here's the first question. It asks to rank the following elements by electron affinity from most positive to most negative. So electron affinity tends to increase negatively this way. So the higher electron affinity value will be up in the halogens, so fluorine. But the noble gases, of course, want to keep their configuration. They don't want any more or less electrons, so those actually will be 0. So right off the bat, we know that neon is going to be pretty much 0, so that guy's going to be our least. Or our most positive value. Now we need to just kind of locate the other guys. So potassium, chlorine, phosphorus, and oxygen. Okay, so then neon is going to be our smallest. Potassium is going to be our next smallest. Phosphorus is then going to be our next smallest. Smallest negative, I should say. And then it's between oxygen or chlorine, which is bigger, larger negative, I should say. So oxygen has a 2s2 2p4 configuration, so it would like to have 2 electrons to fill its octet, while chlorine has a 3s2 3p5 valence. Right, I'm not including the lower shell electrons, meaning with just one more electron it'll be filled. So that means that chlorine will likely have a higher electron affinity, or a larger negative electron affinity than oxygen. So then it likely goes oxygen, then chlorine. Okay, so this is in a negative order. Right, so if we're looking at most positive to most negative, then it'd be actually the reverse. So positive to negative. Although this is 0 and they're all negative. Okay, so looking at the solution, we have electron affinity is the energy released. It's always negative as energy is always released. And so electron affinity becomes less negative down a group. So it gets smaller and increases across. So we get this general trend that I've pointed out. So that noble gases don't want anymore, and the halides are much more. So ranking it the way that I've shown originally, in this way is the better way. So neon is less than potassium, is less than phosphorus, is less than oxygen, is less than chlorine. So the solution is correct. All right. I'm going to leave it here. All right, and so for my second question here, it wants to write the electron configuration for a few cations and a few anions. Specifically, these are quite deep in the table here. So strontium is over here. Cesium plus is here. Indium is over here. And lead is down here. Okay, so for when we're writing the electron configuration, I always find it's easiest to just run along the table. And so remember, first of all, that helium should really be here as far as the blocks go. So we have our S block, our P block, our D block, and our F block. And remember that the F block really goes in here. So these guys go in here. All right. So for strontium, we have 1s2, and then nothing, and then 2s2, and then 2p6, and then 3s2, and then 3p6, and then 4s2, and then for the D block, we hold 10, but it starts at 3D, and so there's 10, and then 4p6, and then we get up to strontium, so we've got 5s2. All right, so that's our electron configuration for strontium. Now if we want to do 2+, well, we just remove 2 electrons. And we always remove the outer shell ones, so then that's our strontium 2+. Now repeating this for indium, or cesium, sorry. So again, we've got our 1s2. So cesium's down here. So it's pretty much got the exact same configuration of strontium. 2s2, 2p6, 3s2, or at least it has all the beginnings of strontium, I should say. It's a whole other shell down. And then 5s2. And then now we go to 4d. So 4d10. And then 5p6, sorry. Yep. And then 6s1. And now again we want to get the positive. So we just remove this outer electron. And now for indium. Well, indium is over here, so it is strontium plus the d electrons. So all the way up to here, 5s2. 4d10, 5p1. So we want indium plus, so we just remove one of the outer electrons, and there we go. And then to get lead, we continue down the line. So 1s2, 2s2, 2p6, 3s2. And we keep going pretty much up to where cesium is, and then go a bit further. Okay, so then 6s2. And now the F block comes in, and like the D block, it doesn't start at the same number, but for the F block it actually starts 2 less, so it's going to be 4F, and there's, if you count them, 14. So there's 14 there. And then the D block, so that's 5d10, and then the P block, 6p2. And then we want 2 plus, so we just cut out 2 electrons. And so then there's our electron configuration for lead 2 plus. Now for the anions, actually for the anions, I'm just going to erase this. So there's all our cations, and like I said, we just count across. Alright, and I'm just going to erase all this. And so now the anions it wants are just phosphorus, sulfur, and bromine. So for phosphorus, again, remember that helium should really be over here. So we have 1s2, 2s2, 2p6, 3s2, and 3p3. Now to get the 3 minus, we need to add 3 electrons, not take away 3 electrons. So instead of 3, we now have 6. So it actually has the same, my periodic table has an H for argon. Has the same configuration as argon. Okay, so then the next one is S. So for sulfur, it's pretty much right next to phosphorus, so it's 1s2, 2s2, 2p6, 3s2, and then 3p, counting right up to where sulfur is, 4. Now to get 2 minus, we add 2 electrons. And so it's the exact same configuration. And now for bromine, we've got our 1s2, 2s2, 2p6, 3s2, 3p6, so all the way across, and then 4s2, and 3d10, and then 4p5. And then to get the minus, we just add 1 electron, so instead of 5, this becomes 6. Okay, and so there's our anion electron configurations. Okay, so here's the solution. So the f orbitals actually don't have 16 electrons, they can hold 14. You can just get it by just counting. And then yes, we can write it as in condensed. I find it much easier just to count across, which is basically what this is showing. If we look back, or think back, so these are the configurations we had for our strontium, our cesium, and our indium. The lead here is missing the F block, so that's not so great. But then for phosphorus, sulfur, and bromine, this looks good. So it's really just the lead is missing its F block. But I would say the solution is largely correct. F block can only hold 14, not 16 electrons. And the lead configuration is missing F block electrons. But it's, I would say, basically correct. Okay. All right. So now for this one, how would you determine the ml quantum number? Okay, so in an atom, our electronic states are numbered by a few quantum numbers. So before we get to ml, there's n, which is our principal quantum number. And this guy goes from 1, 2, 3 up to infinity. And this basically numbers the states and is what defines our energy. So in a hydrogen atom, well, largely defines our energy, I would say. In a hydrogen atom, right, the energy is minus R over N squared, so that's the N. And so whatever state you're in, that's what the principal quantum number is. And so 1 is the lowest and infinity is the highest. Okay, so L is our orbital momentum quantum number. And this can be roughly thought of as shape for our orbital. So L goes from 0 up to n minus 1. So again, it takes integer values, but it only goes up to n minus 1. So if n equals 0, L only equals 0. If n equals 1, then L can be 0 sorry, there we go, that was, threw me for a second. If n equals 1, sorry, L can only equal 0. If n equals 2, then L can only be 0 or 1. Now the L quantum number is typically relabeled as our SPDs, right? So if L equals 0, that's an S. If L equals 1, that's a P. If L equals 2, then that's a D. Or if L equals 3, then that's an F. Right? So that's the reason why there's only a 1s subshell. There's no 1p, so on and so forth. That's why there's only 2s and 2p, no 2d, no 2f. That's why you only get up to 3d, and that's the reason why you only get up to 4f here. If L increases further, then we would just call them, we would just follow alphabetical order. So L equals 4 is G, 5 is H, so on and so forth. But in our periodic table, we only get up to F shells, or we only observe electrons in F shells. Although with excitation, we can hit more exotic shells. Especially in molecules, I should say. Okay, so now we've got N and L. So then ML is our magnetic quantum number, or our azimuthal. And this is largely direction. So ML is minus L up to plus L. So it takes on every value from minus L to plus L. So in an S subshell, so L equals 0. So in S shell, ML equals 0, right? It can only have the value 0. So that's the reason why we only have one S shell, which can hold 2 electrons, as there's 2 spin quantum numbers that can differentiate them. And in an L equals 1 shell, so a P shell, ML equals minus 1, 0 or 1. That's the reason why we get 3 P shells, each being able to hold 2 electrons for a whole total of 6 electrons. In an L equals 2 shell or a D shell, we have ML equals minus 2, minus 1, 0, 1, 2. That's the reason we get 5, which can hold a total of 10. And in an F shell, we have ML minus 3, minus 2, minus 1, 0, 1, 2, 3. And That's why we get 7 total orbitals. So 3, 4, 5, 6, 7, which can each hold 2 for a total of 14 electrons. Okay. So those are our ML values, which are possible. How you would actually determine an ML value is actually not really possible, as the electrons are going to be inhabiting many of these in a superposition, and so they're not really that meaningful. They just define the orbitals which are possible. Okay, so then this kind of defines, along with the MS values, which I didn't talk about, but that's just the spin on the electrons. And okay, so I would say this is correct. So it defines the ML values, so the solution is correct. Okay. All right, so here we have an H-like ion, which contains only one electron, has energies like in the hydrogen atom, both a small modification. So and then a Z squared over N squared, where that is our atomic number. And that's our principal quantum number there. Okay. And Z's the atomic number. So it wants, the question is looking for the ionization energy for helium plus. So helium should have 2 electrons. Helium plus only has 1 electron. So helium would be a 2s2. As it's plus, it's just 2. No, it wouldn't. Helium would be a 1s2. But because it's helium plus, then it's just 1s1, which is the same as hydrogen. So it's a hydrogen-like ion, meaning its energy levels are given by this expression. The ionization energy, or the first ionization energy, and only if you only have 1 electron, is given by the difference between infinity and your highest orbital. In this case is just 1, as it only has a 1s1. So that would be minus 2.18 times 10 to the minus 18 joules. Z squared we can take out, and for helium will be 2, as it's the second element. So 2 squared. And then that'll be 1 over infinity squared minus 1 over 1 squared. And so 1 over infinity is 0, so that goes to 0. And so we get a minus 1, which is going to cancel with our negative out front, giving us 4, so that's 2 squared, times 2.18 times 10 to the minus 18 joules, which equals 8.72 times 10 to the minus 18 joules. It also wants the answer in kilojoules per mole, so that means We need some conversion factors. So a kilojoule is 1,000 joules. And to get into per mole, we just need to multiply by Avogadro's number. So I'm going to try to make it less messy. So Avogadro's number is 6.022 times 10 to the 23. 1 over moles are the units on it. So that'll give us our kilojoules per mole. And then if we run this through our calculator, we get an ionization energy for helium plus of 5251.184 kilojoules per mole. All right, and I guess we're not really given any significant digits because everything's a constant, but I guess we're only given 3 significant digits on the Rydberg constant, so I suppose it would be 5250, but I'm just leaving everything in there. So this looks good. Okay, 1 cubic meter of aluminum has a mass of 2.70 times 10 to the 3. The same volume of iron. So we're really given 2 densities here. So our density of aluminum is 2.70 times 10 to the 3 kilograms over 1 meter cubed. Our density of iron here is 7.86. And so we're asked to find the radius of a solid aluminum sphere that will balance a solid iron sphere of radius 2 centimeters on an equal iron balance. So we're looking for what radius of an aluminum sphere would have to have the same mass as an iron sphere with a radius of 2 centimeters. So volume of a sphere is 4/3 pi r cubed, and that's going to get us to our mass through our density that we're given in the question. So for our iron sphere, it's 4/3 pi times 2.00 centimeters cubed. We're going to want everything in meters cubed, so we should multiply this then by 1 meter per 100 centimeters cubed. So this equals 4/3 pi 8 times 1 meter cubed over 6 centimeters cubed. And so then that equals 3.351 times 10 to the minus 5 meters cubed. Okay, so then that's our volume. Using our density above, we can get a mass. So our mass of iron is then this, our density factor, which we're given in the question. Times this volume. And so you can see that the meters cubes cancel, giving us kilograms. So 0.26339 kilograms. Now this must equal our aluminum mass for it to balance. So then our mass of aluminum is also this number. And this has to, and we can get our volume. We can get our total volume by using our density factor again. So our volume for our aluminum is this mass times 1 over our density factor, 2.70. And you can see that the kilograms cancel, leaving us with a volume unit, 9.7552 times 10 to the minus 5 meters cubed. And now with our sphere equation, we can solve for r, right? So v equals 4/3 pi r cubed. So that means that r cubed is 3v over 4 pi. Subbing in our volume now. We get that r cubed is 2.329 times 10 to the minus 5 meters. Taking the cube root, r is 0.02856, or r equals 2.86 centimeters. I forgot the meters in there. So that's just doing a quick unit conversion with 100 centimeters per meter. So then there's our final answer. So R is 2.86 centimeters. So that's the radius of our aluminum sphere. So checking to the solution here. So looks good. And so 2.86 is what comes out. So that looks good. So solution is correct. Okay. So what are the structural isomers of C3H9N? So all of our structural isomers are going to be some different configuration of these elements around the molecule, not symmetric versions, so not swapping, but just different in different positions in the molecule. So since there's hydrogens, we know are going to be kind of tagged on the end, and the carbon backbone might interchange with the nitrogen, but basically these things are going to define our structure. So we could have something which looks like this, just running through basically. So I largely do it by just guessing and then seeing what comes out. Remember that nitrogen wants to have 3 bonded entities, whereas carbon wants 4. So there's 3, 6, 7, 8, 9. So there's C3H9N, so that looks good. So now swapping the position of the nitrogen and the carbon. So we have 3, 4, 5, 6, 7, 8, 9, so that looks good. So these two are isomers. So now I've kind of swapped them in the chain. Now looking at branches, so we could have C, C, N. And we can count up the hydrogens here, 3, 6, 7, 8, 9. So that looks good. And it's different from these two. So we can't stick it on the end here because that would just be the same. And so instead, we can swap the position of these two. And so we'd get something like this. And I believe that's about it. That's about all I can think of. So again, there's not really a great rule of thumb that I have for how to know how when you've gotten enough structural isomers, other than that the constituents that can multiply bond are going to need to move throughout the structure. So, and in this case, I just tried the nitrogen as an end and as a swapped with the end basically, and then coming off of the center and swapped, and then from there it's just going to be the same molecule over and over again, right? So if you try to move the nitrogen over to this guy, well, that's just the same as the ones above. So it looks like there's 4 structural isomers, all the ones that I've shown here. So if we look at the solution here, so we've got nitrogen coming off the end, so that's my isopropylene, or sorry, propylamine. And then right below it is the isopropylamine here. And trimethylamine is this guy, or sorry, N-ethylamine is this guy, and then my trimethylamine is down here. Okay, and so those are the 4 that I found, and so I believe that's it, and that's. So I believe this is correct. Okay, so what type of intermolecular force of attraction is found in CO2? So so CO2 would be a molecule like this. And it's linear, meaning that although there might be a dipole between, or although there is a dipole between a carbon atom and an oxygen, it cancels. So there's no dipole, and there's no hydrogen atom, meaning that our 2 strongest forces, which are the dipole-dipole forces and H bonding, don't exist in this molecule, so there's no dipole-dipole or H bonding forces. So the only thing left are the London dispersion. And so those are the forces that will dominate with carbon dioxide. No dipole-dipole and H bonding. So the only thing left is London dispersion. So it looks good. what is the H3O plus and pH what is the H3O plus concentration and pH of a 0.1 molar benzoic acid solution. So our equation here, or yeah, our chemical reaction is going to be an acid base, so it's going to be add water, and we're going to go to H3O plus plus C7H6, nope. So we're going to donate a hydrogen, so it should be H5O2 plus. I'm just going to migrate this down a little bit, or a lot. There you go. Okay, so, all right. And it's given that our Ka is 6.5 times 10 to the minus 5. And then our starting concentration is 0.100 molar. Now, to find our concentrations at equilibrium, we can use our ice table. Right, so initially we have 0 of this and 0 of this. Water is our solvent, so we don't need to consider that. The concentration of that species, as it basically doesn't change. Oops. So the change is going to be minus X. And everything's at a 1-to-1 mole ratio, so that means we're going to add X. And so then at equilibrium, we have 0.1 minus X, X, and X. And so our Ka is concentration of H3O plus, concentration of that should be minus. Concentration of C7H5O2 minus over our concentration of C7H6O2. And these are at equilibrium, so these are X, X, and 0.1 minus X. As our Ka value is so small, likely our X value is going to be small, and so the approximation here is that 0.1 minus X is approximately 0.1. And so then we can simplify things greatly by doing that, because now we have 6.5 times 10 to the minus 5 times 0.1. Actually, I'll just do it fully. Is equal to X squared over 0.1. And so then solving for X squared here, we have X equals the square root of 6.5 times 10 to the minus 6. So solving the square root, we get X equals 2.55 times 10 to the minus 3 molar. Okay, which kind of validates that assumption, as 0.1 minus this is going to be approximately 0.1. And so our pH is the negative logarithm of our H3O plus concentration, which I should say, right, our X from our ice table is our H3O plus concentration. So that means we were solving directly for our H3O plus concentration. And so our pH is the negative logarithm of our X, or the negative logarithm of 2.55 times 10 to the minus 3 molar, or 2.59. Okay, so we can work through this, and I guess some rounding error gave us a difference of 0.01, but that's okay. And so I'll say the solution is correct. So that looks good. Okay, a compound NiX3 is 19.67% by mass nickel. So that means the molar mass of nickel is 0.1967 times the molar mass of our NiX3 species. All right, so the mass of the element is 19.67%, or the mass of nickel is 19.67% the mass of the species. So it wants the molar mass of the compound and the name of the compound. So to get the molar mass of the compound, we just rearrange this expression and solve using the molar mass of nickel, which is 58.6934. Which comes out to be 298.39044 grams per mole. And now to figure out what the X species is, the molar mass of the X species is 298, is this molar mass, minus our molar mass of nickel, as there's only one nickel in the substance. And then divided by 3, as there are 3 X species in there. So the molar mass for our X species comes out to be 79.8999 grams per mole. So about 79.9. If we check the periodic table, then the mass of bromine is 79.904 grams per mole. Now to guide your search a little bit, I would say this looks like a compound in which nickel is likely 3 positive, and so we're looking for something that's singly negative, which would be one of the halogens. Yeah, so the mass of bromine is about 79.904, so likely X is Br, and so our species is then NiBr3, which would be nickel 3 bromide, as nickel is 3 positive in this molecule. And then we get about 79.9, and it looks like it's nickel bromide, or nickel 3 bromide. So this is correct. Looks good. Okay, calculate the pH of a 0.2 molar solution of KCN. Okay, and for this question as well, or to expand on it, we're also going to use the Ka for HCN is equal to 6.2 times 10 to the minus 10. Okay, so KCN is a salt, and so we're going to assume that it 100% dissociates into K plus Cn minus. Okay, now the cyanide ion is a base, so it reacts with water to give us HCN, which is our acid, plus OH minus. Now, given the Ka for HCN, we can get the Kb because the relation between Ka and Kb is Kw, where given a Ka for an acid, Kb is the equilibrium for the base. Or put another way, Ka would be concentration of Cn minus. No, I'm not going to do that because I just realized that's not going to work. Okay. Yeah, so Ka is the acid equilibrium constant, and Kb is the conjugate base constant. Oh, right, I see. I remember now. So if we have our Ka for HCN, then Kb is then Kw over Ka. Kw is 1 times 10 to the minus 14. It's just a constant. So 1 times 10 to the minus 14 over Ka, which is 6.2 times 10 to the minus 10. And so then this equals 1.6129 times 10 to the minus 5. Okay, so now we can use our ice table to calculate our equilibrium. Okay. And so we have our initial concentration of Cn minus, which we're assuming is the full concentration of our HCN. And 0 and 0. Our change is minus x plus x plus x. So our equilibrium is 0.2 minus x. I should say I'm only using minus. They're all 1 to 1 in the chemical expression. So that's why it's just minus x and plus x. If there was any numbers, any stoichiometric coefficients, then these would be multiplied by those relevant factors. But for this, it's just like that. And so that means our Kb is equal to our HCN concentration, our OH minus concentration, over our Cn minus concentration, all at equilibrium. These are our equilibrium values, so just x times x over 0.2 minus x. And then, as we've done many times before, to simplify things, I'm going to assume that this is just 0.2, as x is going to be very small because our Kb is also very small. Now putting in our values, We have 1.6129 times 10 to the minus 5 is equal to x squared over 0.2. X squared is equal to 3.22. I should just, yeah, so just multiplying by 0.2, we get 3.2258 times 10 to the minus 6, or x is equal to 1.796 times 10 to the minus 3 molar. And so looking at our ice table above, x is our OH minus concentration at equilibrium. For pH, we want our H3O plus concentration. So recalling that our Kw factor comes from this expression. Okay, where Kw is equal to our OH minus concentration times our H3O plus concentration, which means with our OH minus concentration, we can calculate our H3O plus. So our H3O plus concentration is then just 1 times 10 to the minus 14, which is Kw, over our OH minus concentration, which comes out to be 5.568 times 10 to the minus 12 molar. And so then our pH is the negative logarithm of this value, which is 11.25. So there's our pH for that solution. Okay, I'm going through here, so in here they actually solve for the POH, and then we can, just like here how we're solving for H3O plus concentration, you can use this relation instead to solve for pH. It's really the same, just a different direction. But that looks good, so the solution is correct. And I'm going to stop it there and say that's all my questions for today. I hope you enjoyed it. If you did, please subscribe to the OneClass channel. If you want to add questions, please follow the links below the video. And this has been Jeff Krause for OneClass, and I hope to see you.